All right, so in the last video, we talked about span. And in this video, I kind of want to work up to a more formal definition of basis, why we care about it. And in doing so, talk a little bit about linear independence and also dimension of a vector space. So this video is going to be pretty definition heavy, just as a warning, so brace yourself. But we're going to go ahead and just start off with the definition of span from the last video. So we said that if we have a set of vectors v1, v2 up through vk that live inside of a vector space, then we say that they can span the vector space if you can write any vector v that already lives in the bigger vector space v in terms of the other vectors here as a linear combination of them. So as long as you're able to find some c1, some c2, up through some ck that allow you to do this for every vector v in your vector space v, then you're good to go. You have a spanning set. But you may be thinking, is this the best I can do? What if I have more vectors than I need in my spanning set? And you might want to trim down your spanning set as much as you possibly can. So to write this out, you need to ask yourself, do you need all of the vectors v1, v2 up through vk to be able to span v? Or can you get rid of some? And if you can get rid of some, how many exactly can you get rid of? How many do you have to keep around? So to answer this question, we have to consult something called linear independence. So if you're watching this video in May 2020, which I imagine most people are, then you've seen this definition a whole bunch of times already. But just to give you a reminder, we say that a set of vectors, and remember, these are just going to be random vectors, not necessarily a spanning set. But a set of vectors, v1, v2 up through vk, is said to be linearly independent if we can write the linear combination of them out like this. No, we're using k's, ck, vk. If we want it to equal 0, then the only way we're able to get that is if we have the trivial solution. C1 is equal to C2 is equal to CK is equal to 0. So the only way we're able to have this homogeneous equation here is if all the coefficients are equal to 0. So what this tells us then is that all of the vectors v1 up through vk cannot be written in terms of each other. So v1, v2 up through vk. That's not how you spell that. Cannot be written in terms of each other. And so why do we care about that? Well, it means then that each of these adds something new to the table. So each one of these provides some new information about our vector space that we didn't have before. And so we need to keep them around in order to describe our vector space. So, you might think, okay, well, how many of these do I actually need now? I know what I need them to be. They need to be linearly independent, but how many of them do I need? And so we introduce something called dimension as another vocab word we're going to cover in this video. And this dimension literally just means the amount of linearly independent vectors you need I hope that's spelled right, to span your vector space. So this is not something you'll ever really have to solve for. It's something that the textbook gives you. So in section 4.6, they give you a list of dimensions for common vector spaces. So one of them, for instance, is the dimension of Rn, so n-dimensional real space. You need n linearly independent vectors to describe that. So as an example then, like if we have R2, I need at least 2 vectors here, 1, 0, and I don't know, 1, 2. Those work. But if I add a third one in here, I still definitely span the set, right? But I don't need it because I can do a better job. So this brings us to our next definition here of basis. So a basis is the best spanning set you can have. What does that mean? It means that you're able to still get to everything in V, which means that your basis V1, V2 up through Vn spans your vector space, so that's still fine. But you also don't have any extra information in there. You only have the vectors you need to do so, and so you have linearly independent vectors that are in your spanning set. So pretty much what you've done then is you started with a spanning set all the way up here. You've taken a look at it. You've said, okay, I need a particular number of them, your dimension of them, in order to span my vector set in the best way possible. So you look at your spanning set and you just get rid of all of your linearly dependent vectors until you can no longer do so. And once you've done that, you're left with a linearly independent set, and you have a basis for your vector space. So I know this was a lot of writing and not a lot of math, but hopefully this was able to refresh your memory a bit on the difference between span and basis.